Greetings, scholars. Beautiful Mind here. We're continuing our exploration on Chapter 3 on functions, and here we're going to be looking at Section 3.2, Domain and Range. A few learning objectives. In this section, you will find the domain of a function defined by an equation and graph piecewise defined functions. So, crafting unforgettable adventures. Consider Adventure X, a company providing exhilarating journeys to unique global destinations. As enthusiasms for their adventures rises, more adventurers eagerly join. Adventure X monitors participation rates and considers variables such as destination and difficulty to predict demand and customize their experiences. For instance, challenging mountain treks appeal to seasoned hikers, while family-friendly safaris attract larger groups during holiday periods. By comprehending these patterns, with the aid of functions and understanding domain and range, Adventure X crafts unforgettable experiences for a broad range of adventurers. This section will delve into techniques for assessing the domain and range of analogous functions. So, this is some of the ways that we'll express solution sets, right? You might see X is greater than A. These are just some of the ways, and these will come out naturally as we kind of progress. I just wanted to include this slide in the presentation, but we'll come back to this, right? But these will come out in different examples that we work. So in this first example, we're asked to find the domain. We're looking at finding the domain of a function of a set of ordered pairs. We're asked to find the domain of this function. So our domain is going to be our set of input values, right? So in this context, our inputs, so these are called ordered pairs, like our X, Y, I think like we had in the previous section. So our domain is going to be our set of inputs, or in other words, our set of X values, right? So we have 2, 3, 4, 5, 6. So then our domain in this case would be the set 2, 3, 4, 5, and 6. Okay, so I think we got that one. So given a function written in equation form, we want to see how to find the domain. So identify the input values, identify any restrictions on the inputs, and exclude those values from the domain, and then write the domain in interval form if possible. So that first slide that we had, where we had all the graphs, that kind of showed us how we go from set builder notation to the graph form, and then finally to interval notation, right? And again, we'll work several examples where we're going to be doing that. So let's see, in this example, we're asked to find a domain. So with something like this, this is a polynomial, right? A polynomial takes on the form where you have some real number coefficient times a variable raised to a non-negative integer power, right? Here, let me back up. So a polynomial is a finite sum of monomials, and a monomial is a term or expression that takes on the form you have some real number coefficient times a variable raised to a non-negative integer power. So examples of monomials would be things like 2x squared, 5x to the power of 12, 3, stuff like that. Those are all examples of monomials. And then a polynomial is just a finite sum of those guys, all right? So we have a real coefficient times some variable x raised to a non-negative integer x. Same thing with this guy, all right? So once we identify a function as a polynomial, the domain of polynomials is all reals. If we were to graph this guy, this would be a U-shaped curve that we shifted down by 1. Sorry, I just drank some water before I started and it went down the wrong pipe, and I can't, I'm still struggling to kind of straighten it out. If you wanted to graph this, there's a couple of ways that you can graph this right now. You can make a table of values, choose several values of x, find the corresponding y's, plot the points, and connect them with a smooth curve. If you have a TI-83 Plus graphing calculator, you can put this into your y equals portion and look at the graph. As long as you can access the internet, which you should be able to do because this is a remote course, you can use a site that's called Desmos.com. I think I've mentioned this before, where it's a free online graphing utility. So you can use Desmos.com. You could also use GeoGebra.com. to look at the graph. And so in a graphical sense, the domain is the very left to the very right, all the possible values that x can take on, right? So again, we identified this as a polynomial, and in general, the domain of a polynomial is all reals, so this domain is going to be all reals. Okay. Okay. So another, any real number x is gonna, we can plug it in and find the corresponding y in this example. So given the function written in equation form that includes a fraction, we want to find the domain. Okay, let's see this. I'd rather just see this in action. So this one, we're asked to find the domain of this function. I'll write it here. I'll get a copy of it. On bottom, we have this 2 minus x. On top, we have x plus 1. And again, this is our f of x. So this is what's called a rational function because we have a variable x, or we have a variable in the denominator. So in general, for a rational function, the domain is going to be all reals except when it comes to fractions. The main thing whenever we're working with fractions, what is it that we're on the lookout for, right? Just take a moment to think to yourself, what number can we not divide by whenever we're working with fractions, right? Hopefully you're thinking 0, right? We cannot divide by 0 whenever we have fractions. So that extends to finding the domain of a rational function. In general, the domain of a rational function is going to be all reals except any x that makes the denominator 0. Right. So if we set the denominator to 0 and solve, that'll tell us the x. Let me see. So for instance, when x is 2 here, then it makes a 0 in the denominator. So the domain for this guy is going to be all real numbers except 2. Right. So set bundle notation, we might capture it like x is not equal to 2. Right. And if we want to capture everything except 2, let me see the graph of that. Would look something like this. So say here's our 2. If we want everything except 2, we want all the numbers to the right of 2. In addition, we want all the numbers to the left of 2. All right. And then because we don't want to include 2, the grouping symbol we're going to use are parentheses, right? So we use parentheses. The parentheses means we get we get infinitesimally close to this number, like we get really close to the number, but we don't include the number, right? So this would be the graph of this. And then to translate from the graph to interval notation, the far left is what? Negative infinity? So the far left is negative infinity up to 2. And then on the other side, it goes from 2 to infinity. Infinity always gets the grouping symbol parentheses. Because we don't want to include the 2, these 2's get parentheses. And we combine these two sets with this symbol called union. Right? So we're saying that any number chosen in these either left of 2 or right of 2 will work in the original context. But if we try to choose 2 itself, it won't work. Let me see, I'm a little bit out of space. I'm going to go like this. And I guess I can center it since I'm done. Okay. So when we say x is not equal to 2 in interval notation, we're basically saying everything except 2, and this is how we capture that. Okay. So I think in our graph, we use parentheses going in opposite directions. We can also capture that by, it's a solid line, but then there's an open circle at the 2. The open circle is synonymous to the parentheses, right, in this context. Okay. So in the previous example, we looked at a special case with the rational functions. Again, in general, for a rational function, the domain is all reals except any x that makes the denominator 0. So then here, when we take an even root like square root, We can't take the square root of what kind of numbers, right? We can't take the square root of negative numbers, right? So in general, for an even root, that radicand, the part inside the radical, has to be non-negative, strictly greater than or equal to 0, right? So again, because we can't take the square root of negatives, the radicand, which is going to be the 7 minus x, has to be greater than or equal to 0. Then if we solve this inequality, add x on both sides, we get that 7 is greater than or equal to x. So then that's let's look at the graph of that. Okay. Say this is our 7. If the alligator eats the bigger thing, that means our numbers are smaller than 7, right? So we're talking about numbers going in this direction. Okay. And then because we have a bar, and let me color code it to help it pop. I guess we'll do like purple. So because that bar is there, that means we're going to use a square bracket. And so what the square bracket means versus the parentheses, in the previous example, parentheses meant what? We get really, really close to that number, but we don't include the number. Whereas square bracket means not only do we get really, 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 really close to that number, but we do include that number, right? So this would be the graph, and then to convert from the graph to interval notation, the far left is negative infinity up to 7. Again, in this context, infinity always gets parentheses because we never reach it, and the 7 gets a square bracket. And also, like in the previous example where we may have seen it as an open circle on the line graph, in this context you might see it as a closed circle. Let me resize this again. I don't know how I had the same issue with the sizing. And I'm going to go ahead and center it. Okay. Oh yeah, so I did notice where my discussions kept showing the same topic. That was just my fault. So like, again, I think I mentioned this in the previous one, but anybody that like submitted it, I just went on to give them credit, but it should be different topics. I was changing it in the description, but it wasn't changing in the actual topic itself. So I had to change it in multiple locations for it to work properly. So, but again, as long as that's really just a check-in. I just need people to do it just to make their presence known. Since we don't meet synchronously, we need some way to kind of log attendance. And so that's why we have those discussions. So it's okay. And they're supposed to be light, not so light we're supposed to be repetitive, but I was like, why does it seem like we're talking about the same thing every week? And I know when I'm changing these things. So anyway, I think I got to the bottom of it. So we'll see. I changed as many of them as I could based on whatever it was not already due. Okay. So we got from negative infinity up to 7 with a square bracket. Yes, that's correct. Let me see. So in the previous examples, we use inequalities and lists to describe the domain of functions. We can also use inequalities or other statements that might define sets of values or data. So this is kind of like reiterating what we were kind of experiencing. So we have this graph form, right? Inequality notation. So h is strictly greater than 5, but less than or equal to 10. And then set builder notation. And, you know, so like, for instance, when we were solving, we would get a result, something like this. Then we would create the corresponding graph, and we would finish with the interval notation, right? So we kind of and we'll keep exploring these as we go along. So set builder notation is a method of specifying a set of elements that satisfy a certain condition. It takes the form the set of all x such that the statement about x is true, right? So for instance, the set of all x such that 4 is less than x, which is less than or equal to 12. So interval notation is the way of describing the sets that include all real numbers between a lower limit that may or may not be included and an upper limit that may or may not be included. The endpoint values are listed between brackets or parentheses. A square bracket indicates inclusion in the set, and parentheses indicates exclusion from the set. So in this example, this is saying we don't include 4 and we do include the 12. And we want all the numbers between those. Okay, let's see an example. Another one anyway. Describe the interval of values shown in this figure using inequality notation, set builder notation, and interval notation. Okay. So for the first part on the left, our x is what? Greater than or equal to 1 and less than or equal to 3, or x is what? Strictly greater than 5, and that's it. All right, because it's an arrow. It just keeps going over to the right. Okay, so if that's inequality notation, then this would be what? In a set builder notation, this would be the set of all x such that, then we repeat that. I think I'm making a little bit of a mistake, but x is between 1 and 3 inclusive, or x is strictly greater than 5. Okay. And then in interval notation, it should be, let me see, we're talking about all the numbers from 1 to 3. We include those endpoints, so we use a square bracket, union from what? 5 to positive infinity. Infinity always gets a parentheses, and because we don't include the 5, that gets a parentheses as well. Okay, let's see, how do we do? I think we got that. Did we get the or? Yeah, we got it all. Yeah. Okay, we're making pretty good time. All right, let me see what the text says here. So another way to identify domain and range of a function is by using its graph. Because the domain refers to the set of possible input values, the domain of the graph consists of all input values shown on the x-axis. So, and then the range is the set of possible output values, which are shown on the y-axis. And you do have to keep in mind that the graph continues beyond the proportion that we can see. The domain and range may be greater than the visible values, right? Okay, so you have to keep in mind that the pattern continues based on, like for instance, this one has a closed circle, so that's an endpoint. But this end has an arrow, so that means the pattern continues indefinitely, right? So in a graphical sense, the way I usually remember it is the very left to the very right. How far left does the graph go? How far right does the graph go? Okay. So find the domain and range. Now, if I'm looking for the domain, and I'm considering the very left to the very right, I'm gonna okay. So the very left to the very right, right? How far left does it go? The far left, it gets infinitesimally close to -3. And then how far right does it go? It goes all the way to 1 and includes 1. So then the domain of this guy, it should go from where -3 to 1. Because there's an open circle, it means we don't actually reach the -3, we get close, so we use the parentheses. And because on the 1 we have a closed circle, that means that's going to get a square bracket. Okay, so the domain is the very left to the very right. So then the range is going to be the very bottom to the very top. Okay. So when we're trying to find the range, we ask ourselves, how far down does the graph go? The very bottom, the graph doesn't go below y equals -4. And the very top, looks like it's x equals 0 because of the max there. So then the range being the very bottom from the very top, the very bottom looks like it's -4. The very top looks like it's 0. We actually do reach the -4, so that gets a bracket. And because at the origin, it looks like we pass through the origin, that means that we will use a bracket of 0 as well. All right. So the domain -3 to 1 and the range -4 to 0. Okay. Sorry, it's like early in the morning. Okay, we're about halfway. So find the domain and range of this function given. So the domain, I guess I can just, I'll just do it. So the very left, how far left does this go? What year is that? Let me see if those are going by 5s. I can't tell if that's the year because it doesn't look like it's 1970. I feel like we might need some more information. Because each tick mark is going by 5 years, but the spacing looks weird. So whatever that far left one is, all right? Okay. So then let's actually just capture this from 1975 to 2005, right? So the very left we'll say is 1975. And I'm doing this because it kind of went off to the right as well. And so, it's kind of weird. So I'm going to say the domain is going from 75 to 2005. And then the range is the very bottom to top. Now it's an approximation. It's above halfway, so and it's fairly close to 200. So maybe I would say like approximately like 180 to something that's slightly above 2,000. Let's look at the prepared notes. 73. Okay, so it does go. So the inputs were slightly to the left of 1975, so I think they let it be 1973. And then slightly to the right of 2005, I think they did like 2008. Yeah. 1973. And then 180 to 2010, right? So those were approximations just because the way the data was displayed. Okay. Oh, shoot. Okay, well, this one said, can a function's domain and range be the same? Yeah, for example, the domain and range of a cube root function are both the set of all reals. Okay, so I think last time we introduced this library of parent functions or base functions. I think that this book refers to these as toolkit functions. So the book, whenever the book says toolkit functions, you might hear me say it as either basic functions or parent functions, right? So those are some of the ways I've seen it described. So then we want to consider, with this little exercise, the domain and range of each of the following. So for instance, the first base function that we had was the constant function. So if we have a flat horizontal line, the domain being the very left to the very right looks like it's what, all reals. And then the range being the very bottom to the very top is just y equals c. It's just going to be c. Okay, so we got that correct. The domain is all reals. They did it kind of weird. They did a square bracket from c to c, but that just means just the number c, just that one number. So then the second example is the first column on the second row. We have the identity function, y equals x. The domain, if we consider the very left to the very right, is going to be what? All reals, and then the very bottom to the very top is all reals. So both of those are going to be all reals. And then let me see, row 1, column 2 is the absolute value function. Domain, the very left to the very right is going to be all reals. The very bottom, how far down does the graph go? So the lowest it goes is here. That y value is what, y equals 0. And how far up does it go? It goes up to infinity. So the range would be 0 to infinity with a square bracket on the 0. Okay. And I acknowledge the print is small, but the main takeaway here, I just wanted to do an exercise on domain and range. And then next with the squaring function, it's a parabola, quadratic function. The domain is the very left to the very right, which is all reals. The range is the very bottom to the very top. It goes down to the origin. So that would be 0 to infinity. So I think it's the same as the previous example. And then first row, third column. Cubing function, domain is all reals and the range is all reals. For the reciprocal function, the very left to the very right. So the domain, the far left is negative infinity here, right? But then we have this vertical asymptote where it crosses over and it doesn't touch. And then it continues on to positive infinity on the other side. Okay. So then the domain here is going to be everything except 0. All right. And the range, I think, is a similar argument. If you consider it from the very bottom to the very top, is everything except 0. Okay. And you see it here. And then the first row, fourth column, that's the reciprocal squared function or squaring function. The domain being the very left to the very right, everything except 0. The range, the very bottom is to the very top, is going to be 0 to infinity with an open, with the parentheses on the 0. Sorry. Okay, so then second row, column 4, that's a square root function. The domain being the very left to the very right, so it looks like it goes from 0 to infinity. And the range, it looks like it's also 0 to infinity. And then the cube root function, domain and range are both all reals. Okay. All right, so let's see what else we have. Man, these presentations are intense. Oh. In that, like, I'm building these PowerPoints from scratch, and then I have to turn around and do a video presentation on it. Like, part of the reason I'm so tired, I was making this PowerPoint for a few hours, and then I'm trying to finish it because I'm supposed to meet with the student in 30 minutes remotely, and so I'd like to finish this, and which I think I'm within range. I mean, it's going pretty good as far as the rhythm, but that's part of the reason I'm so sleepy. I've been working on this for hours. And then I still need to do at least one more before, ASAP, one more section. So anyhow, before the week is out. And I have the intent to do a bonus lecture like a fool, give myself more work. But I want to have that in my catalog, so I'm gonna just go ahead and do it. Given the formula for a function, we want to see how to determine the domain and range. Okay, I'm gonna just kind of work it. Let's see. Let me see what it says actually. Exclude from the domain any input values that result in division by 0. Exclude from the domain any input values that have a non-real or undefined number output. Okay. Find the domain. This is what, a cube function? We don't have any restrictions. It's a polynomial. So the domain and range are both here, should be all reals. And you see it here. Okay. Find the domain. Again, for reciprocal functions, in general, the domain is all reals except any x that makes the denominator 0. So again, here we're starting with what we have, this x plus 1, 2 equals f of x. All right. So the domain here, everything is, again, for rational, the domain in general is all reals except any x that makes the denominator 0. So when x is -1, that makes the denominator 0. So long story short, we want to capture everything except -1, and we do the following. Infinity always gets parentheses. Because we do not want to include -1, we use parentheses, and we combine these two sets with the union. Okay, let's keep going. We're almost done, actually, so it seems like it's going a lot faster than I anticipated, which is good. I'm okay with that. Oh, I forgot about the range. So this was our domain. Let's see. So with this being a reciprocal function, there's actually a 3-pronged test that we can do for the range here. And we would have to compare the degree of the numerators. For you all, I would encourage you to just maybe right now, just look at the graph. But you should notice that the x-axis serves as a horizontal asymptote. So then y equals 0. So in other words, let me think. I think so we would want everything except 0 for the range. Let me see. Let's just kind of go with it. There are some other techniques that we can do, but I think we have to kind of explore a little bit more before we can talk about them. And that's really supposed to be a U. It's just my handwriting is bad. It's a union. Let me see. Yeah. Because the function is never 0, we exclude 0 from the range. We have some other techniques for solving there, but for you all, again, I would just look at the graph. You should notice a horizontal asymptote. You kind of have to be looking for asymptotes when you're working with reciprocal functions. Again, I use this 3-pronged test where I compared the degree of the numerator to the degree of the denominator. And because the degree of the numerator was less than the degree of the denominator, I had a horizontal asymptote at y equals 0. But, you know, for that one, again, the very bottom to the very top is everything except y equals 0. Okay. So then for square root functions, again, we can't take the square root of negatives. So that means that the radicand has to be greater than or equal to 0. So this x plus 4 has to be greater than or equal to 0. So then x is greater than or equal to -4. Okay, so in interval notation, it's going to be from -4 to infinity. It gets a square bracket, that's the domain. So for square root functions, in general, the range goes from 0 to infinity. We did not move it up or down at all. I think we stretched it vertically, but we didn't move it up and down. So that range is going to go 0 to infinity. And the 0 gets a square bracket because, you know, when x is -4, we actually include, you know, y equals to 0. So -4 to infinity, 0 to infinity. Okay. We're almost there. So a piecewise function is a function in which more than one formula is used to determine the output. Each formula has its own domain, and the domain of the function is the union of all these similar domains. We notate this idea in this following manner. In piecewise notation, the absolute value function is going to be x if x is positive or greater than or equal to 0, and negative x if x is negative. Okay, I'm going to let that be. So let's look at this example on writing a piecewise function. A museum charges $5 a person for a guided tour with a group of 1 through 9 people, or a fixed $50 fee for a group of 10 or more people. Write a function relating the number of people n to the cost. So the cost depends on the number of people. So we can say something like the cost based on a number of people. Let me see, it's $5 per person. So it's 5n if n is like the number of people, if the group is from 1 to 9. So that applies when n is greater than or equal to 1, but less than or equal to 9. But then it says it's a fixed $50 fee for groups of 10 or more. So we can do something like when n is strictly greater than 9. And so this is a piecewise function, right? Two separate domains. And basically, like we're basically like comparing multiple functions in one go. Okay, I feel like this is okay. Five n if n is, okay, they did 0 to 10. We did greater than or equal to 1 or less than or equal to 9. That's fine. And then if n is greater than or equal to 10, that's fine. Okay, we're going to let that be. A cell phone company uses the function below to determine the cost in dollars for gigabytes of data transfer. Find the cost using 1.5 gigabytes of data and the cost of using 4 gigs. Okay. So if we use 1.5 gigs, that means that one's going to apply to the first line because 1.5 is between 0 and 2. So the net cost is going to be what? $25. Okay. So the cost of using 1.5 gigs is going to be $25. And then the cost of using 4 gigs, so that's going to apply to the second row. 4 minus 2 is 2, times 10 is 20, plus 25 is 45. I plugged in 4 into the second equation. Okay, so these are the results that we got. $25 and $45 is correct. Yeah, sorry guys, my energy is so low. Okay, so to sketch the graph of a piecewise, essentially what you do is you graph all the functions like normal, but then you restrict it down to its proper domain, right? And the domain tells you, what to keep and what to get rid of. So sketch the graph. I think I'm just going to do a rough graph. I'm not going to use grid paper and be super precise. If I can get this to work. Okay, so this is my positive x. My x is it just goes from 1 to 2. I'm not sure about my y, so I'll go kind of like this. This will be my positive y in this direction. So, for instance, I'll do the first one in blue. So x squared, maybe I should use graph paper. Let me see. So we have 1, 2, 3, 4, 5, 6, 7. That's too much, but that's okay. 1, 2, 3, 4, 5, 6, 7. Okay, so I'm going to try it on the rough sketch. So for instance, when x is 1, y is 1. I know that's part of the first one. When, and then going over to the left. So it's basically a parabola, like a shape like this. And it just continues in that direction. And then the second one, it says y equals 3 whenever x is between 1 and 2. So 1 and 2. We'll do that one in green. So 1 to 2 is 3. Let me see. X cannot be equal to 1. So that means we're going to use an open circle here. But it can be equal to 2. So then we use a closed circle there. And then connect those with a straight edge. Okay. And then the third part, whenever x is strictly larger than 2, y equals x. So then, like for instance, when x is 2, y is 2, and we start off with an open circle there. And then y equals x. It's just this. Oh, and let's, we'll use a different color. I'll pick a color in just a moment. I mean, that's fine. And I guess we'll do that one. We'll do that one in purple. Okay. So essentially, like what I did, I graphed the parabola like normal, but again, the domain says this only applies when x is less than or equal to 1. So I just kept the part to the left of 1 and used the proper grouping symbol. In this case, it was like a closed circle, or the proper endpoint, should I say. And then for the middle one, that's just a flat horizontal line, y equals 3, but it only applies when x is between 1 and 2. I did an open circle on 1 because there's no bar here, and a closed circle on 2 because there is a bar there. And then for the third one, it's just y equals x as a diagonal, but it only applies when x is strictly larger than 2. So I'm talking about to the right of 2, we get this image. Okay. And so you can see a computer generated portion here where they kind of did each one individually, and then they should put them together, right? They put them all together, and I think we got a similar image. Okay, that wasn't too terribly bad. And I messed up on this one too. Can more than one formula form a piecewise function be applied to a value in the domain? No, each value corresponds to one equation in the piecewise function, right? So it still has to pass the vertical line test, right, for functions. Okay, so with that, we're going to go ahead and end this session here. And from one beautiful mind to another, take care. Peace.